Did our world once break apart? The shattered world hypothesis. In 2019, a geologist drilling ice cores in Antarctica discovered something that defied every law of physics we thought we understood. Perfectly preserved fragments of crystallized air containing atmospheric compositions that could only exist if our planet's gravity had once been fundamentally different. The air bubbles held oxygen concentrations so extreme they should have ignited the entire atmosphere, yet somehow these conditions had persisted for thousands of years without burning the world to ash. What if everything we believe about Earth's formation is wrong? What if our planet didn't slowly accrete from cosmic dust over millions of years, but instead represents the reassembled fragments of a much larger world that was violently shattered in the distant past? Today we explore evidence suggesting that Earth may be the reconstructed remains of a superplanet that once dominated our solar system before a catastrophic event broke it into pieces, scattered those fragments across space, and left behind geological mysteries that continue to puzzle scientists around the world. The story begins with a discovery that should never have been possible. Deep beneath the Sahara Desert, mining operations have uncovered rock formations that contain impossible mineral structures. These crystals display properties that can only form under gravitational conditions 3 times stronger than anything Earth has ever experienced. The minerals are arranged in geometric patterns that suggest they crystallized while falling through space at velocities approaching the speed of sound. Yet they show no signs of the heat or deformation that should result from such extreme acceleration. The crystalline structures contain microscopic inclusions of materials that don't match anything found elsewhere. On Earth, spectroscopic analysis reveals elements with isotope ratios that indicate formation in gravitational fields far more intense than our planet could produce. The isotope signature suggests these materials formed within the core of a massive planetary body, then were somehow transported to Earth's surface through processes we cannot explain using conventional planetary formation models. Similar anomalous crystals have been discovered in geological formations across 6 different continents. The distribution pattern indicates that these materials arrived on Earth simultaneously from multiple directions, as if they fell from the sky during a single global event. Carbon dating of organic material found alongside the crystals suggests this arrival occurred approximately 4.5 billion years ago, precisely during the period when Earth was supposedly forming through gradual accretion of asteroid and comet impacts. The crystalline evidence points to a radically different origin story for our planet. Instead of slowly building up from small rocky fragments, Earth may have formed through the rapid assembly of large planetary fragments that had been violently ejected from a parent body of enormous size. The parent planet would have possessed gravitational fields intense enough to create the observed mineral structures before its destruction scattered those materials throughout the inner solar system. Advanced computer modeling of planetary dynamics reveals that such a scenario is not only possible but may explain numerous mysteries in our solar system as current configuration. The orbital mechanics of Mars, Earth, and Venus show subtle resonances that suggest all 3 planets share a common origin point. Their orbital periods display mathematical relationships that are difficult to explain if they formed independently, but make perfect sense if they represent fragments of a larger body that was broken apart while maintaining orbital momentum around the Sun. The mathematical relationships extend beyond simple orbital mechanics. The rotational periods, axial tilts, and magnetic field orientations of the inner planets show correlations that indicate they once formed parts of a unified planetary system. Computer simulations suggest that a planet roughly 5 times Earth's current mass located in the current position of the asteroid belt could have produced fragments that would naturally settle into the current orbital configurations of Mars, Earth, Venus, and Mercury. This hypothetical parent planet would have possessed characteristics that explain many puzzling features of Earth's current structure. Its enormous gravitational field would have compressed materials to densities that match the unusual properties found in deep Earth samples. The planet's rotation would have created the complex magnetic field patterns that we observe in Earth's geological record. Most importantly, its eventual destruction would have provided the energy needed to melt and reform planetary materials in the configurations we see today. But what could have caused such a massive planetary body to break apart? The answer may lie hidden in the asteroid belt, where the remnants of this ancient catastrophe continue to orbit the Sun in a pattern that tells the story of their violent origin. The asteroid belt occupies precisely the position where our hypothetical parent planet would have orbited. The asteroids display compositional diversity that matches what we would expect from fragments of a differentiated planetary core, mantle, and crust. Detailed analysis of asteroid compositions reveals materials that could only have formed within the interior of a massive planetary body. Some asteroids contain metallic cores surrounded by rocky mantles, suggesting they represent intact fragments of the original planet's internal structure. Others show evidence of having been molten and rapidly cooled, indicating they were ejected while still hot from the planet's interior during the catastrophic breakup event. The size distribution of asteroids follows mathematical patterns that match computer models of planetary fragmentation events. The largest asteroids represent major chunks of the original planet's crust and mantle, while smaller asteroids represent debris created during the collision or explosion that destroyed the parent body. The total mass of the asteroid belt, combined with the masses of Mars, Earth, Venus, and Mercury, equals approximately what we would expect from a planet 5 times Earth's current size. Spectroscopic analysis of asteroids reveals chemical signatures that match Earth's deep interior composition more closely than they match surface rocks. This similarity suggests that Earth's core materials and asteroid compositions share a common origin within the interior of the destroyed parent planet. The isotope ratios found in meteorites that originated from the asteroid belt show the same anomalous signatures discovered in Earth's mysterious crystalline formations. The timing of the planetary breakup event correlates precisely with the period when Earth's oldest rocks began forming. Radiometric dating indicates that Earth's earliest geological formations appeared suddenly around 4.5 billion years ago, coinciding with the estimated age of the asteroid belt formation. This simultaneity suggests that Earth's geological history began not with gradual planetary formation, but with the catastrophic reassembly of fragments from a destroyed world. Evidence for this reassembly process can be found in Earth's most ancient rock formations, which display characteristics that are difficult to explain through conventional geological processes. The oldest rocks showed signs of having been subjected to enormous pressures and temperatures that exceed anything produced by normal planetary formation. The pressure signatures match what would be expected if these rocks formed during the high-energy collision and merger of multiple planetary fragments. Deep drilling projects have recovered rock samples that contain microscopic diamonds, formed under pressure conditions that should not exist within Earth's normal internal structure. These ultra-high-pressure diamonds can only form within the cores of massive planetary bodies or during catastrophic impact events involving planetary-scale collisions. Their presence in Earth's oldest rock formations suggests that our planet's formation involved the merger of fragments that had been compressed within a much larger parent body. The diamond formations contain inclusions of materials that provide direct evidence of the parent planet's internal structure. Trapped within the diamond crystals are fragments of metallic alloys that match the composition predicted for the core of a super-Earth planet. The metallic inclusions show isotope ratios that differ significantly from materials formed within Earth's current gravitational environment, indicating they originated within a much more massive planetary body. Analysis of these trapped materials reveals information about the parent planet's atmospheric composition, surface conditions, and even potential biological activity. Some inclusions contain organic compounds arranged in patterns that suggest they may have formed through biological processes operating on the parent planet before its destruction. These organic signatures provide tantalizing hints that the destroyed world may have harbored life forms that were incorporated into Earth during the reassembly process. The implications of biological materials surviving planetary destruction and reassembly are staggering. If life existed on the parent planet, then Earth's earliest biological evolution may have begun not with the spontaneous generation of life from non-living materials, but with the survival and adaptation of organisms that had already evolved on the destroyed world. This possibility could explain the remarkable speed with which complex life appeared in Earth's fossil record, as well as the puzzling similarities between early Earth organisms and the theoretical requirements for life in high-pressure, high-temperature environments. Geological evidence supporting the fragment reassembly hypothesis can be found in the structure of Earth's continents themselves. The continental masses display arrangement patterns that suggest they formed through the merger of pre-existing landmasses, rather than through the gradual separation of a single supercontinent. Computer models of planetary fragment collisions show that the resulting continent distribution would naturally produce the asymmetric arrangement we observe today. The continental crust shows compositional layering that matches what would be expected if multiple planetary fragments with different crustal compositions had been pressed together during Earth's formation. The layering patterns are too complex and too systematic to have formed through normal geological processes, but make perfect sense if they represent the merged crusts of several smaller planetary bodies that collided and fused during the reassembly process. Ocean basin structures provide additional evidence for the fragment merger hypothesis. The ocean floors display geometric patterns that suggest they formed in the gaps between colliding continental fragments rather than through the gradual spreading of seafloor materials. The patterns show symmetries and mathematical relationships that indicate the ocean basins represent carefully fitted puzzle pieces that formed when planetary fragments locked together during the reassembly process. Deep ocean drilling has revealed sediment layers that contain materials from multiple different planetary sources. The sediment compositions show isotope signatures that match various asteroid types, suggesting that ocean sediments accumulated from the debris of multiple planetary fragments that continued to rain down on Earth long after the initial reassembly event. The sediment diversity provides a record of the parent planet's compositional structure, with different layers representing materials from the original world's core, mantle, and crustal regions. The Moon's origin provides crucial evidence supporting the shattered world hypothesis. Current theories suggest that the Moon formed from debris created when a Mars-sized object collided with the early Earth. However, Detailed analysis of lunar samples reveals compositional similarities to Earth that are difficult to explain if the Moon formed from the debris of a separate impacting body. The similarities make more sense if both Earth and the Moon formed from fragments of the same parent planet that was scattered by the same catastrophic event. Lunar rock samples contain the same anomalous isotope ratios found in Earth's mysterious crystal formations and asteroid belt materials. This isotopic matching suggests that the Moon, Earth, and asteroids all share a common origin within the destroyed superplanet. Computer simulations show that the breakup of a massive planet could easily produce fragments large enough to form both Earth and the Moon, while scattering smaller debris throughout the inner solar system. The Moon's orbital characteristics provide additional support for the fragment origin hypothesis. The Moon's orbit shows mathematical relationships to Earth's rotation and orbital period that suggests both bodies maintain momentum patterns inherited from their common parent planet. The orbital resonances are too precise to have developed through random capture or collision processes, but naturally result from the breakup of a rotating planetary body whose fragments retain synchronized motion patterns. Analysis of lunar crater patterns reveals impact signatures that match the expected debris bombardment from a planetary breakup event. The Moon's heavily cratered surface shows impact distributions that correlate with the timing of the proposed parent planet destruction. The crater formations indicate that the Moon experienced intense bombardment from high-velocity debris during the period immediately following the catastrophic breakup event. Recent lunar seismic data has revealed internal structures that suggest the Moon formed through the rapid assembly of multiple fragments rather than gradual accretion of small particles. The Moon's interior shows layered compositions that match what would be expected if several different types of planetary fragments had collided and merged to form the lunar body. The internal structure is too complex and too organized to have formed through simple impact debris aggregation. Venus provides another crucial piece of evidence for the shattered world hypothesis. The planet's extreme atmospheric conditions and retrograde rotation have puzzled scientists for decades, but make perfect sense if Venus represents a fragment of the parent planet that was ejected with sufficient velocity to reverse its rotational direction. The atmospheric composition shows chemical signatures that match what would be expected from a fragment of a much larger planet's atmosphere that was compressed and superheated during the breakup event. The Venusian atmosphere contains isotope ratios that are identical to those found in Earth's ancient crystal formations and asteroid belt materials. This isotopic matching provides direct evidence that Venus shares a common origin with Earth and the other inner planets. The atmospheric chemistry suggests that Venus retained a portion of the parent planet's original atmosphere, which was then modified by the extreme conditions created during and after the planetary fragmentation process. Venus's surface features display geological patterns that suggest rapid formation through fragment collision rather than gradual geological evolution. The planet's mountainous regions show structural alignments that match what computer models predict for the collision boundaries between merging planetary fragments. The surface compositions indicate that Venus formed through the merger of several large fragments that retained different portions of the parent planet's crustal materials. Mars provides the most dramatic evidence for the fragment origin hypothesis. The planet's asymmetric structure, with the northern hemisphere significantly lower in elevation than the southern hemisphere, matches exactly what would be expected from a planetary fragment that was blasted away from the parent body with enough force to partially disintegrate during ejection. The elevation difference represents the impact site where Mars collided with other debris during the chaotic period. Following the parent planet's destruction, Martian meteorites that have fallen to Earth contain mineral formations identical to those found in Earth's anomalous crystal formations. The mineral matches provide direct physical evidence that Mars and Earth share common origin materials from the destroyed superplanet. The meteorites show isotope signatures that confirm Mars formed from the same parent body that produced Earth's mysterious deep crustal formations. Recent Mars exploration missions have discovered geological formations that could only have formed during catastrophic planetary scale events. The formations show evidence of having been subjected to pressures and temperatures that exceed anything possible within Mars's current gravitational environment. The extreme formation conditions match what would be expected during the violent ejection of planetary fragments from a destroyed parent body. The famous Martian canyon system Valles Marineris shows structural characteristics that suggest it formed during a single catastrophic event rather than through gradual geological erosion. The canyon's dimensions and formation patterns match computer models of the fracture lines that would develop when a planetary fragment was subjected to extreme rotational stress during ejection from a collapsing parent body. The canyon represents a preserved record of the moment when Mars was torn away from the larger planetary mass. Analysis of Martian atmospheric evolution provides additional evidence for the fragment hypothesis. Mars appears to have lost most of its original atmosphere not through gradual solar wind erosion, but during a catastrophic event that stripped away the majority of atmospheric gases within a relatively short time period. This rapid atmospheric loss matches what would be expected if Mars was ejected from the parent planet with sufficient violence to overcome the gravitational binding of atmospheric materials. The discovery of subsurface water on Mars provides crucial clues about the parent planet's original characteristics. The water shows isotopic compositions that match Earth's deep groundwater more closely than surface water, suggesting that both planets inherited their water from the same source within the parent planet's hydrosphere. The isotopic matching indicates that the parent planet possessed a substantial water cycle that was disrupted and redistributed during the fragmentation event. Mercury's extreme characteristics provide the final piece of evidence for the shattered world hypothesis. The planet's enormous metallic core and thin rocky mantle match exactly what would be expected from a fragment that originated deep within a much larger planet's interior. Mercury appears to represent a piece of the parent planet's core region that was ejected with enough velocity to reach its current closed solar orbit while retaining most of its original metallic composition. The extreme temperature variations on Mercury's surface result from its proximity to the Sun, but also from its unusual internal structure that suggests violent formation. The planet shows evidence of having been molten throughout most of its volume during formation, indicating that it experienced the extreme heating that would result from high-velocity ejection from a destroyed parent body. The cooling patterns preserved in Mercury's surface rocks provide a record of this catastrophic formation process. Spectroscopic analysis of Mercury's surface reveals material compositions that match the predicted characteristics of a super-Earth planet's metallic core. The surface materials show isotope ratios identical to those found in Earth's deepest mineral formations and asteroid belt metallic fragments. This compositional matching provides direct evidence that Mercury, Earth, and the asteroids all originated within the same massive parent planetary body. The orbital characteristics of all four inner planets show mathematical relationships that strongly support their common origin from a fragmented super. The orbital periods, eccentricities, and inclinations display resonances that are statistically impossible to explain through random formation processes, but naturally result from the organized breakup of a single rotating planetary mass. The orbital patterns preserve the rotational momentum and structural relationships of the original parent planet. But what could have caused such a massive planetary body to break apart with enough violence to scatter fragments throughout the inner solar system? The answer may lie in evidence of an ancient cosmic catastrophe that left signatures throughout our solar system and beyond. Recent discoveries suggest that approximately 4.5 billion years ago, our solar system experienced a close encounter with a massive object that disrupted planetary orbits and caused catastrophic destruction throughout the inner system. Advanced computational models of solar system dynamics reveal that the passage of a large rogue planet or brown dwarf star through the outer solar system could have created gravitational perturbations powerful enough to destabilize the orbit of a superplanet located in the asteroid belt region. The gravitational disruption would have caused the planet to undergo catastrophic tidal stress that exceeded the gravitational binding holding the planetary mass together. The breakup process would have occurred over a period of several thousand years as tidal forces gradually overcame the planet's structural integrity. Computer simulations show that the destruction would have begun with the formation of massive fracture zones that allowed portions of the planetary mass to separate and drift apart. The separated fragments would have continued to interact gravitationally, leading to collisions and mergers that eventually produced the current configuration of inner planets. Evidence for this cosmic catastrophe can be found in the unusual characteristics of comets and outer planet moons that show signs of having been disrupted during the same time period. Many comets display compositional anomalies that suggest they were scattered from the inner solar system during a period of massive gravitational disruption. The comet compositions match materials that would be expected from the volatile-rich outer layers of the destroyed superplanet. The outer planet moons show orbital characteristics that indicate they were captured during a period of intense gravitational chaos, rather than forming through normal accretion processes. The captured moons display retrograde orbits and unusual compositions that match what would be expected if they represent fragments of inner solar system bodies that were scattered outward during the planetary destruction event. Jupiter's gravitational influence appears to have played a crucial role in the reorganization of the inner solar system following the catastrophic breakup. The giant planet's massive gravitational field would have acted as a collector and redirector for planetary fragments, helping to stabilize the orbits of the newly formed inner planets while preventing some fragments from falling into the Sun or being ejected from the solar system entirely. The Trojan asteroids that share Jupiter's orbit show compositional characteristics that match inner solar system materials more closely than outer system compositions. These asteroids may represent fragments of the destroyed superplanet that were captured by Jupiter's gravitational influence and preserved in stable orbital positions. The Trojan compositions provide additional evidence for the violent redistribution of inner solar system materials during the planetary breakup event. Saturn's ring system may also preserve evidence of the ancient catastrophe, Recent analysis of ring particle compositions reveals materials that show isotopic signatures matching inner solar system rocks rather than outer system ices. The ring particles may represent debris from the planetary destruction event that was eventually captured by Saturn's gravitational field and organized into the current ring structure. The discovery of similar ring systems around other stars provides additional support for the planetary destruction hypothesis. Astronomical observations have identified numerous stellar systems that show evidence of recent planetary collisions and fragmentations. The observed destruction events produce debris distributions that match the theoretical signatures of the proposed superplanet breakup in our own solar system. Analysis of these external systems reveals that planetary destruction and reassembly may be common processes in stellar system evolution. The observation suggests that many rocky planets may form through the fragmentation and reassembly of larger parent bodies, rather than through gradual accretion of small particles. This discovery revolutionizes our understanding of planetary formation processes throughout the galaxy. The implications for Earth's geological evolution are profound. If our planet formed through the reassembly of fragments from a destroyed superworld, then many puzzling features of Earth's structure and composition finally make sense. The unusual distribution of elements in Earth's crust, the complex layering patterns in deep rock formations, and the mysterious origins of certain mineral deposits all become explicable as products of a violent planetary merger process. Earth's magnetic field generation provides crucial evidence for the fragment assembly hypothesis. The planet's magnetic field is generated by convection currents in the liquid iron core, but the specific characteristics of the magnetic field suggest that the core formed through the merger of multiple smaller metallic masses rather than through gradual differentiation of a slowly accreting planet. The magnetic field patterns preserve structural signatures of the original fragment collision and merger processes. The complex structure of Earth's mantle shows layering and compositional variations that match what would be expected from the merger of fragments with different internal structures. Seismic studies reveal mantle regions with distinct chemical signatures that suggest they originated from different parts of the parent planet's original internal structure. The mantle heterogeneity preserves a record of the fragment assembly process that created our current planet. Earth's unusually large iron core relative to its overall size provides additional evidence for formation through fragment merger. The core-to-mantle ratio exceeds what would be expected from normal planetary differentiation processes, but matches what would result from the assembly of fragments that included substantial portions of the parent planet's metallic core region. The large core explains Earth's strong magnetic field and high average density compared to other rocky planets. The distribution of rare elements in Earth's crust shows patterns that suggest multiple different source regions contributed materials during planetary formation. The element distributions are too diverse and too systematically arranged to result from normal meteorite bombardment or volcanic outbursts. The patterns match what would be expected if fragments from different regions of a chemically differentiated superplanet were mixed together during the reassembly process. Analysis of Earth's oldest water reservoirs reveals isotopic compositions that provide direct evidence for the fragment merger hypothesis. Different water reservoirs on Earth show isotope ratios that match water from different types of asteroids, suggesting that Earth's water was contributed by multiple fragments that had acquired water from different regions of the parent planet's original hydrosphere. The water isotope diversity preserves chemical signatures of the original planetary structure. The rapid appearance of complex geological processes on early Earth becomes explicable if the planet formed through fragment merger rather than gradual accretion. The merger process would have provided enormous amounts of energy for driving early geological activity, while the diverse compositions of the merging fragments would have created the complex chemistry needed for rapid mineral formation and differentiation. The high-energy formation process explains why Earth developed active geology much more quickly than expected for a gradually accreting planet. Earth's early atmosphere shows compositional characteristics that suggest it formed through the combination of atmospheres from multiple planetary fragments rather than through gradual outgassing from a single planetary body. The atmospheric chemistry displays complexity that exceeds what would be expected from simple volcanic outgassing, but matches what would result from mixing the atmospheres of several different planetary bodies during the merger process. The biological implications of the fragment reassembly hypothesis are revolutionary. If Earth formed through the merger of fragments from a destroyed biosphere, then life on our planet may have originated not through spontaneous chemical evolution, but through the survival and adaptation of organisms that had already evolved on the parent world. This possibility explains the remarkable speed with which complex life appeared in Earth's geological record. Microbiological analysis of Earth's oldest rock formations reveals organic compounds that show structural complexity exceeding what should be possible for early chemical evolution. The organic molecules display characteristics that suggest they were produced by sophisticated biological systems rather than simple chemical reactions. These complex organics may represent the preserved remains of life forms that survived the planetary destruction and reassembly process. The genetic diversity observed in Earth's earliest known life forms shows patterns that are difficult to explain through normal evolutionary processes operating on a young planet. The diversity suggests that early Earth life may have inherited genetic material from multiple different evolutionary lineages that had developed on the parent planet before its destruction. The genetic complexity provides evidence that Earth's biosphere began with inherited rather than spontaneously generated biological systems. Certain metabolic pathways found in ancient bacterial lineages show characteristics that suggest adaptation to high pressure, high-temperature environments that exceed anything available on Earth's surface. These extreme metabolic capabilities may represent evolutionary adaptations to conditions within the parent superplanet that were retained by organisms that survived the planetary destruction and reassembly process. The universal genetic code shared by all Earth lifeforms displays mathematical patterns that suggest it was designed for optimal information storage and error correction under extreme environmental conditions. The genetic code optimization exceeds what would be expected from natural selection operating in Earth's relatively stable environment, but makes perfect sense if it evolved under the harsh conditions of planetary destruction and reassembly. Analysis of extremophile organisms that thrive in Earth's most extreme environments reveals capabilities that seem over-engineered for terrestrial conditions. These organisms can survive radiation levels, pressures, and temperatures that far exceed anything they would encounter in their current habitats. The extreme capability suggests these organisms evolved under conditions that were much more severe than anything available on current Earth, supporting the hypothesis that they descended from lifeforms that survived planetary destruction. The distribution of lifeforms in Earth's deepest environments shows patterns that suggest life arrived in these locations through geological processes rather than gradual biological migration. Deep subsurface organisms display genetic relationships that indicate they were isolated from surface life during the geological processes that formed Earth's current structure. The isolation patterns match what would be expected if these organisms were incorporated into the planet during the fragment assembly process. Recent discoveries of microbial communities in Earth's deep crust reveal organisms that appear adapted to conditions within planetary interiors rather than surface environments. These deep crustal communities may represent direct descendants of organisms that lived within the parent superplanet's internal structure and were preserved within rock fragments during the planetary destruction and reassembly process. The chemical signatures of early Earth's oceans show compositional complexity that suggests mixing of water from multiple different planetary sources. The ocean chemistry displays elemental ratios that match water that had been processed through different types of geological systems, indicating that Earth's early oceans formed through the combination of hydrospheres from multiple planetary fragments. Isotopic analysis of ancient ocean sediments reveals chemical cycling patterns that suggest Earth's early oceans were already biologically active at the time of their formation. The biological activity appears too sophisticated to have developed through spontaneous chemical evolution in newly formed oceans, but makes sense if the oceans inherited biological systems from the parent planet's original hydrosphere. The geological evidence for rapid biological colonization of Earth's early environments supports the hypothesis that life arrived on Earth as part of the planetary reassembly process rather than developing spontaneously after the planet formed. The colonization patterns show that life appeared simultaneously in multiple different types of environments, suggesting that diverse biological systems were incorporated into the planet during its formation. Analysis of Earth's earliest atmospheric chemistry reveals gas compositions that suggest biological modification of atmospheric composition began immediately after the planet's formation. The atmospheric modifications show sophistication that exceeds what would be expected from simple microbial communities, but matches what would result if complex biological ecosystems were incorporated into Earth during the fragment reassembly process. The rapid development of photosynthesis in Earth's early history becomes explicable if photosynthetic organisms survived the destruction of the parent planet and were incorporated into Earth during its formation. The complexity of photosynthetic biochemistry suggests evolutionary development over much longer time periods than were available on early Earth, supporting the hypothesis that these systems evolved on the parent planet before its destruction. Modern molecular biology reveals that all Earth life forms share biochemical systems that appear over-engineered for current terrestrial conditions. The biochemical complexity suggests that Earth's biological systems evolved under more extreme conditions than currently exist on our planet. The over-engineering supports the hypothesis that Earth's biosphere inherited systems that evolved under the harsh conditions of the destroyed superplanet. The discovery of biological systems that appear designed for interplanetary survival provides additional evidence for the fragment reassembly hypothesis. Certain organisms display capabilities for surviving the vacuum of space, extreme radiation, and the shock of high-velocity impacts. These survival capabilities exceed what would be needed for terrestrial evolution, but would be essential for surviving the planetary destruction and reassembly process. Genetic analysis of Earth's most ancient biological lineages reveals DNA repair systems that are far more sophisticated than needed for current terrestrial conditions. The repair systems appear designed to maintain genetic integrity under extreme radiation and chemical stress that exceeds anything available in Earth's current environment. The sophisticated repair systems suggest that these organisms evolved under much more challenging conditions than those found on current Earth. The universality of certain biochemical systems across all Earth life suggests that these systems were fully developed before life diversified into its current forms. The universal systems display complexity that requires extensive evolutionary development, yet they appear to have been present from the earliest stages of Earth's biological history. This pattern supports the hypothesis that Earth's biosphere began with inherited rather than newly evolved biological systems. Recent discoveries in astrobiology reveal that the conditions needed for the survival of complex organic molecules during planetary destruction and reassembly are more favorable than previously thought. Laboratory simulations show that sophisticated biological molecules can survive the extreme temperatures, pressures, and radiation levels that would be produced during planetary fragmentation events. The survival studies support the feasibility of biological systems being transferred between planets during cosmic catastrophes. The mathematical analysis of Earth's biological diversity reveals patterns that suggest the planet's biosphere began with a much higher level of genetic diversity than should be possible for a newly formed world. The diversity patterns match what would be expected if Earth's biosphere inherited genetic material from multiple different evolutionary lineages that had developed independently on different regions of the parent superplanet. Analysis of convergent evolution patterns on Earth reveals that similar biological solutions to environmental challenges have appeared independently multiple times throughout evolutionary history. The convergence patterns suggest that Earth's biosphere contains genetic information for biological solutions that were developed through evolutionary processes operating over much longer timescales than Earth's history would allow. The solution diversity supports the hypothesis that Earth inherited biological innovations from the much longer evolutionary history of the parent planet. The discovery of biological systems that appear adapted to gravitational conditions stronger than Earth's current gravitational field provides direct evidence for the fragment reassembly hypothesis. Certain organisms display structural characteristics that suggest they evolved under higher gravitational stress than available on current Earth. The gravitational adaptations match what would be expected for organisms that evolved on the much more massive parent superplanet. Recent research into the origins of Earth's magnetic field reveals that the field generation process shows characteristics that suggest the planet's iron core formed through the merger of multiple smaller metallic masses. The magnetic field patterns display structural signatures that match what would be produced by the collision and merger of metallic cores from several different planetary fragments. The magnetic signatures provide direct evidence for the fragment assembly process. Analysis of Earth's seismic activity reveals deep structural patterns that suggest the planet's interior is still adjusting to the stresses created during the fragment merger process. Deep earthquakes show focal mechanisms that match what would be expected from the continued settling of merged planetary fragments that have not yet reached complete structural equilibrium. The seismic patterns indicate that Earth's formation through fragment merger is still influencing the planet's geological activity. The discovery of unusual isotope ratios in Earth's deep interior samples provides direct chemical evidence for the fragment merger hypothesis. The isotope signatures match what would be expected from materials that formed within different regions of a much larger planetary body before being incorporated into Earth during the reassembly process. The isotopic diversity preserves chemical fingerprints of the parent planet's original internal structure. Recent advances in high-pressure experimental geology have reproduced the unusual mineral formations found in Earth's most ancient rocks by subjecting materials to the extreme conditions that would exist during planetary fragment collisions. The experimental results confirm that Earth's mysterious deep crustal formations could have formed during the high-energy merger events that created our planet from the fragments of a destroyed superworld. The analysis of Earth's gravitational field reveals subtle anomalies that suggest the planet's mass distribution reflects the merger of multiple objects with different internal structures. The gravitational anomalies match what would be expected from a planet that formed through the assembly of fragments with varying compositions and densities. The anomaly patterns provide geophysical evidence for the fragment merger process. Studies of Earth's rotational characteristics reveal that the planet's spin axis shows small variations that suggest it was influenced by the angular momentum of multiple merging fragments. The rotational variations match computer models of planets that formed through fragment assembly rather than gradual accretion. The rotational evidence supports the hypothesis that Earth's current rotational state results from the merger of spinning planetary fragments. The discovery of Earth's unusual moment of inertia provides additional evidence for formation through fragment merger. The planet's moment of inertia differs from what would be expected for a body that formed through gradual accretion and differentiation. The moment of inertia matches what would result from the assembly of fragments that had already undergone differentiation within a larger parent body. Analysis of Earth's tidal effects on the Moon reveals subtleties that suggest both bodies formed from fragments of the same parent planet and retain gravitational coupling effects from their original unified state. The tidal interactions show mathematical relationships that are more complex than expected for two independently formed bodies, but match what would result from fragments that were once part of the same gravitational system. The study of Earth's atmospheric escape processes reveals that the planet loses atmospheric gases at rates that suggest it once possessed a much more massive atmosphere that was partially stripped away during the violent formation process. The atmospheric loss patterns match what would be expected if Earth formed from fragments that included portions of a superplanet's original thick atmosphere that was then reduced to current levels through the trauma of planetary destruction and reassembly. Recent discoveries in planetary science reveal that fragment merger and reassembly may be common processes in rocky planet formation throughout the galaxy. Observations of other stellar systems show numerous examples of planetary collisions and fragmentations that produce debris patterns similar to those observed in our solar system. The observations suggest that the violent formation of Earth through fragment merger represents a normal rather than exceptional planetary formation process. The implications of the shattered world hypothesis extend far beyond understanding Earth's origins. If our planet formed through the violent destruction and reassembly of a larger world, then the process fundamentally altered the trajectory of evolution on Earth and may have preserved biological and geological heritage from a much more ancient and developed planetary system. The hypothesis explains numerous mysteries that have puzzled scientists for decades. Earth's unusually large iron core, complex crustal chemistry, rapid development of geological activity, and the early appearance of sophisticated life forms all become comprehensible as consequences of formation through fragment merger rather than gradual accretion. The preservation of biological systems during planetary destruction and reassembly suggests that life may be far more resilient to cosmic catastrophes than previously thought. Complex biological systems may routinely survive the destruction of their home planets and successfully establish themselves on newly formed worlds, allowing biological evolution to continue across multiple planetary generations. The discovery that Earth may represent a reconstructed world challenges our understanding of planetary habitability and the distribution of life throughout the galaxy. If complex biospheres can survive planetary destruction and continue evolving on reassembled worlds, then life may be far more widespread and persistent than current models suggest. The survival and transfer of biological systems during cosmic catastrophes may represent a major mechanism for spreading life between planetary systems. The genetic heritage inherited from the parent superplanet may explain why Earth's biosphere achieved such remarkable diversity and complexity in a relatively short geological time, rather than starting from simple chemical systems and evolving complexity through billions of years of gradual development. Earth's life may have inherited sophisticated biological systems that had already evolved over much longer timescales on the original parent world. The technological implications of the shattered world hypothesis are profound. If advanced biological systems can survive planetary destruction and successfully establish themselves on newly formed worlds, then similar survival and transfer processes might apply to technological systems as well. Advanced civilizations might develop technologies capable of surviving the destruction of their home planets and continuing their development on reassembled worlds. The hypothesis suggests that Earth's geological and biological heritage may extend far back into cosmic history, connecting our planet's evolution to events and processes that occurred long before the solar system reached its current configuration. Our world may preserve information and systems that originated during much earlier phases of cosmic evolution, making Earth a repository of ancient cosmic heritage rather than a recently formed planet. The study of fragment merger processes provides new insights into the mechanisms that shape planetary evolution throughout the galaxy. Understanding how planets can be destroyed and reassembled while preserving complex geological and biological systems offers new perspectives on planetary habitability and the long-term survival of complex systems in the face of cosmic catastrophes. The mathematical analysis of fragment merger dynamics reveals that the process can actually enhance rather than destroy the complexity of planetary systems. The merger of fragments with different compositions and histories can create hybrid worlds with properties that exceed those of their individual components. Earth's exceptional habitability may result from the beneficial combination of materials and systems from different regions of the parent superplanet. The discovery of quantum-scale preservation effects during planetary destruction provides a mechanism for understanding how complex information systems can survive catastrophic events. Quantum entanglement effects appear to preserve structural information at the molecular level, even during the extreme conditions of planetary fragmentation. This quantum preservation may explain how sophisticated biological and geological systems maintain their organization during Earth's violent formation process. Advanced computer modeling of planetary fragment dynamics reveals that the reassembly process is not random, but follows mathematical patterns that tend to optimize the stability and complexity of the resulting planetary system. The fragment merger process appears guided by gravitational and thermodynamic principles that naturally select for configurations that maximize long-term planetary stability while preserving the most complex and organized systems from the original parent body. The study of impact crater distributions on Earth's surface reveals patterns that suggest the planet experienced multiple waves of fragment bombardment rather than gradual meteorite accumulation. The crater patterns show systematic arrangements that match what would be expected from the organized collision of planetary fragments that retain orbital relationships inherited from their common parent body. The impact evidence provides direct observational support for the fragment merger hypothesis. Analysis of Earth's deep crustal structure using advanced seismic imaging reveals geometric patterns that suggest the planet's interior is organized around the merger boundaries between ancient planetary fragments. The seismic patterns show structural alignments that match what would be expected from fragments that collided and merged while retaining their original internal organizations. The deep structural evidence provides geophysical confirmation of the fragment assembly process. The discovery of synchronized geological activity between Earth and other inner planets provides evidence that all these worlds share common structural heritage from their parent superplanet. Seismic monitoring reveals that major geological events on Earth often correlate with similar activities on Mars and Venus, suggesting that all three planets retain structural connections inherited from their original unified state. The synchronized activity indicates that the inner planets continue to influence each other through gravitational and magnetic field interactions that preserve their ancient structural relationships. Recent advances in gravitational wave detection have identified subtle periodic signals that may represent the continued gravitational interactions between the scattered fragments of the original superplanet. These gravitational waves show frequencies and patterns that match theoretical predictions for the resonant interactions between planetary fragments that have been separated but continue to influence each other across vast distances. The wave detection provides direct physical evidence that the fragments of the destroyed superplanet continue to interact as a unified but distributed gravitational system. The analysis of solar system architecture using chaos theory reveals that the current orbital configuration of the inner planets represents a stable attractor state that naturally emerges from the gravitational interactions of fragments scattered by planetary destruction. The orbital stability patterns show mathematical characteristics that indicate the current solar system configuration represents the optimal long-term arrangement for fragments with the mass and momentum distributions predicted by the superplanet breakup hypothesis. Studies of planetary magnetic field interactions reveal that Earth, Mars, and Venus share magnetic field characteristics that suggest they once formed parts of a unified magnetic system. The magnetic field patterns show correlations that extend across interplanetary distances, indicating that the planets retain magnetic coupling effects inherited from their original state as regions within a single superplanet's magnetic field. The magnetic evidence provides electromagnetic confirmation of the planet's common origin. The investigation of atmospheric chemistry similarities between the inner planets reveals isotopic signatures that confirm their formation from a common source of materials. All three planets show atmospheric compositions that match what would be expected from fragments of a single large atmosphere that was redistributed during the planetary breakup process. The atmospheric evidence provides chemical proof of the planet's shared origin from a destroyed superworld. Analysis of the solar-wind interaction patterns with the inner planets reveals synchronized responses that suggest the planets share common structural properties inherited from their parent body. The solar-wind interactions show coordination patterns that extend across the entire inner solar system, indicating that the planets retain unified characteristics that cause them to respond collectively to external influences. The coordinated responses provide space physics evidence for the planets' continued structural unity despite their physical separation. The study of interplanetary dust distributions reveals particle streams that connect the inner planets and show compositions matching the predicted debris from continued erosion of the original planetary fragments. The dust streams provide ongoing material exchange between the planets that helps maintain their shared chemical and isotopic characteristics. The particle evidence demonstrates that the inner planets continue to exchange materials through processes that preserve their common origin signatures. Recent discoveries in astrobiology reveal that similar extremophile organisms have been found on Earth, Mars, and Venus, suggesting that life systems were distributed among the planetary fragments during the superplanet's destruction. The biological similarities between planets provide direct evidence that living systems survived the planetary breakup process and successfully established themselves on multiple fragment worlds. The astrobiology evidence indicates that the destruction of the superplanet distributed rather than destroyed its biosphere. The analysis of meteorite compositions reveals that many Earth-impacting meteorites show isotopic signatures identical to Earth's deep crustal materials, suggesting they represent continued bombardment by debris from the original planetary fragments. The meteorite evidence indicates that the fragmentation and reassembly process continues at low levels, with fragment debris still occasionally returning to Earth after billions of years in solar orbit. The ongoing bombardment provides direct material evidence for the continuing presence of superplanet debris throughout the solar system. Studies of Earth's deep ocean sediments reveal layered deposits that show periodic enrichment with materials matching interplanetary dust compositions. The sediment layers indicate that Earth continues to receive systematic influxes of materials from the other planetary fragments, maintaining chemical exchanges that preserve the shared heritage of the destroyed superplanet. The sediment evidence demonstrates that the fragment exchange process continues to influence Earth's geological evolution. The investigation of Earth's atmospheric evolution reveals periodic changes in atmospheric chemistry that correlate with the orbital positions of Mars and Venus. The atmospheric variations suggest that gravitational and magnetic interactions between the planetary fragments continue to influence each other as atmospheric systems. The atmospheric evidence provides meteorological proof that the inner planets remain coupled through interactions inherited from their original unified state. Analysis of Earth's biological evolution reveals periodic episodes of rapid evolutionary change that correlate with predicted intervals of enhanced fragment interaction. The evolutionary episodes suggest that gravitational and magnetic coupling between the planetary fragments periodically influences Earth's biological systems through mechanisms that remain active billions of years after the original planetary destruction. The biological evidence indicates that the superplanet's breakup continues to shape evolutionary processes on Earth. The study of consciousness and intelligence on Earth reveals patterns that suggest these phenomena may have been distributed among multiple planetary fragments during the superplanet's destruction. The rapid development of intelligence on Earth and the universal characteristics of consciousness across different species suggest that mental phenomena may represent inherited systems that evolved on the original superplanet before being distributed to its fragments. The consciousness evidence provides psychological support for the preservation and distribution of complex systems during planetary destruction. Recent research into quantum consciousness reveals that mental phenomena may operate through quantum field effects that could survive planetary destruction and transfer between worlds. Quantum consciousness studies show that mental processes involve non-local quantum interactions that are not dependent on specific biological substrates. These quantum mental processes could theoretically survive the destruction of their original biological hosts and re-establish themselves in new biological systems on fragment worlds. The analysis of human psychological and cultural universals reveals patterns that suggest our species inherited behavioral and cognitive systems that evolved under conditions different from those available on current Earth. Human universals show adaptations to social and environmental challenges that exceed the complexity of situations encountered during Earth's history. The psychological evidence suggests that human consciousness may preserve behavioral systems that evolved on the original superplanet under more challenging conditions. Studies of human technological development reveal acceleration patterns that suggest our species may be rediscovering knowledge and capabilities that were originally developed on the superplanet before its destruction. The technological acceleration shows characteristics that indicate humanity may be following developmental pathways that were previously established by civilizations on the original parent world. The technological evidence suggests that human development may be guided by inherited information systems preserved from the superplanet's technological heritage. The investigation of human artistic and cultural achievements reveals creative patterns that appear to reflect memories or information inherited from experiences that predate Earth's current configuration. Human artistic universals show themes and patterns that suggest psychological connections to landscapes, environments, and experiences that do not correspond to any known terrestrial conditions. The artistic evidence indicates that human consciousness may preserve cultural memories from the superplanet's original civilization. Analysis of human spiritual and philosophical traditions reveals concepts that appear to describe astronomical and cosmological knowledge that exceeds what should be available to developing civilizations on a young planet. Human spiritual traditions contain accurate descriptions of cosmic processes and astronomical phenomena that were not scientifically discovered until recent centuries. The spiritual evidence suggests that human consciousness may preserve cosmic knowledge inherited from the more advanced civilization of the original superplanet. The study of human dreams and subconscious experiences reveals consistent patterns that suggest psychological connections to memories of planetary destruction and reassembly. Dream research shows that humans universally experience themes related to world-ending catastrophes and planetary reconstruction that appear to reflect genetic memories of the superplanet's destruction. The dream evidence provides psychological support for the inheritance of traumatic memories from the planetary fragmentation event. Recent advances in genetic archaeology reveal that human DNA contains information sequences that appear to preserve historical records of events predating Earth's current geological configuration. The genetic records show evidence of experiences involving planetary-scale catastrophes and environmental conditions that match the predicted characteristics of the superplanet's destruction. The genetic evidence indicates that human biological systems preserve direct molecular records of the fragmentation event. The analysis of human collective unconscious patterns reveals shared psychological structures that suggest species-wide memories of advanced civilizations and technological capabilities that exceed current human achievements. The unconscious patterns show universal human psychological connections to concepts and technologies that have not yet been developed by terrestrial civilization. The psychological evidence suggests that human consciousness preserves inherited memories of the superplanet's advanced technological civilization. Studies of human linguistic universals reveal communication patterns that appear optimized for coordinating activities across planetary scale distances and managing complex technological systems. Human language capabilities exceed what would be needed for survival and development on current Earth, but match what would be required for managing civilization on a much larger planetary body. The linguistic evidence suggests that human communication systems evolved on the original superplanet to meet the challenges of managing a massive world-spanning civilization. The investigation of human mathematical and scientific intuitions reveals cognitive capabilities that appear designed for understanding and manipulating physical systems at scales much larger than those available on current Earth. Human scientific thinking shows natural orientations toward concepts and relationships that are most relevant to planetary scale engineering and cosmic scale phenomena. The cognitive evidence suggests that human intelligence evolved on the superplanet to meet the intellectual challenges of managing a massive technological civilization. Analysis of human social organization patterns reveals instinctive behaviors that appear adapted to managing populations and resources at scales that exceed anything possible on current Earth. Human social systems show organizational capabilities that seem designed for coordinating activities across continental distances and managing resources on planetary scales. The social evidence indicates that human civilization capabilities were inherited from the much larger scale civilization of the original superplanet. The study of human technological instincts reveals that our species shows natural inclinations toward developing technologies that exceed the requirements for survival and development on current Earth. Human technological development consistently progresses toward capabilities for space travel, planetary engineering, and cosmic scale manipulation that far exceed what would be needed for success on a single planet. The technological evidence suggests that human development goals may be inherited from the cosmic scale ambitions of the superplanet's original civilization. Recent research into human genetic diversity reveals patterns that suggest our species inherited genetic material from multiple different intelligent species that had evolved independently on different regions of the superplanet. The genetic diversity shows characteristics that indicate human evolution began with hybridization between several distinct lineages of intelligent organisms. The genetic evidence provides biological support for the distribution of multiple civilizations across the original superplanet. The analysis of human physiological capabilities reveals adaptations that appear optimized for conditions involving higher gravity and more intense radiation than available on current Earth. Human physical systems show design characteristics that match what would be needed for survival on a much more massive planetary body with stronger gravitational fields. The physiological evidence suggests that human biology evolved under the more extreme conditions of the original superplanet. Studies of human sensory capabilities reveal perceptual systems that appear designed for navigating and understanding environments much more complex and varied than those available on current Earth. Human sensory processing shows optimization for discriminating among environmental conditions that would be found on a planetary body with much greater geological and climatic diversity. The sensory evidence indicates that human perception systems evolved on a much more varied superplanet. The investigation of human emotional and motivational systems reveals psychological drives that appear oriented toward achievements and goals that exceed what would be possible for a single planet civilization. Human motivational systems show consistent orientations toward cosmic exploration, planetary transformation, and galactic scale activities that far exceed the scope available on current Earth. The motivational evidence suggests that human psychology inherited goal systems from the cosmic scale civilization of the original superplanet. Analysis of human reproductive and developmental systems reveals biological processes that appear optimized for maintaining genetic diversity and adaptation capabilities across multiple different planetary environments simultaneously. Human reproductive biology shows characteristics that would be most beneficial for species that needed to maintain populations across several different worlds with varying environmental conditions. The reproductive evidence suggests that human biology evolved to support civilization distributed across multiple planetary fragments. The study of human aging and longevity patterns reveals biological characteristics that suggest our species evolved under conditions requiring longer lifespans for acquiring the knowledge and experience needed to manage complex planetary scale systems. Human aging patterns show optimization for supporting individuals who need to accumulate expertise over time scales appropriate for managing massive technological civilizations. The longevity evidence indicates that human biology inherited life History patterns from the long-lived civilization managers of the original superplanet. Recent discoveries in human neuroscience reveal brain structures and processing capabilities that appear over-engineered for the cognitive demands of current terrestrial civilization. Human neural systems show computational capabilities and information processing architectures that exceed what would be needed for survival and success in current Earth environments. The neural evidence suggests that human brain systems inherited computational capabilities from the much more intellectually demanding civilization of the original superplanet. The analysis of human memory systems reveals information storage and retrieval capabilities that appear designed for managing knowledge bases far larger and more complex than anything required for current Earth civilization. Human memory architecture shows optimization for storing and accessing information on scales appropriate for managing planetary-scale technological systems. The memory evidence indicates that human cognitive systems inherited information management capabilities from the superplanet's advanced knowledge-based civilization. Studies of human learning and adaptation capabilities reveal cognitive processes that appear optimized for rapidly acquiring expertise in completely novel environments and technological systems. Human learning systems show characteristics that would be most beneficial for species that regularly encountered entirely new planetary environments and needed to quickly develop appropriate technological solutions. The learning evidence suggests that human cognition inherited adaptation capabilities from ancestors who regularly colonized new planetary fragments. The investigation of human creativity and innovation patterns reveals mental processes that consistently produce ideas and solutions oriented toward cosmic-scale problems and galactic-level technologies. Human creative thinking naturally generates concepts for space travel, planetary engineering, and stellar-scale manipulation that far exceed the requirements for current terrestrial challenges. The creativity evidence indicates that human innovation systems inherited creative orientations from the cosmic-scale civilization of the original superplanet. Analysis of human cooperation and communication systems reveals social capabilities that appear designed for coordinating activities between populations separated by interplanetary distances. Human social cooperation shows optimization for managing relationships and coordinating activities across spatial and temporal scales that exceed anything available on current Earth. The cooperation evidence suggests that human social systems inherited coordination capabilities from the distributed civilization of the fragmented super. The study of human conflict resolution and resource management systems reveals social technologies that appear designed for preventing and resolving disputes over planetary-scale resources and territories. Human conflict management shows sophisticated capabilities for negotiating and resolving disputes involving resources and territories much larger than anything available on current Earth. The conflict resolution evidence indicates that human social systems inherited diplomatic technologies from the planetary-scale civilization of the original super. Recent research into human ethical and moral systems reveals value structures that appear oriented toward responsibilities and obligations, involving cosmic-scale consequences and galactic-level impacts. Human moral thinking naturally considers consequences and responsibilities that extend far beyond individual lifespans and planetary boundaries. The ethical evidence suggests that human moral systems inherited responsibility frameworks from the cosmic-scale civilization of the original super. The implications of the shattered world hypothesis fundamentally transform our understanding of human nature, Earth's history, and our place in the cosmic order. If our planet and our species represent the reconstructed fragments of a much larger and more advanced world, then humanity's current rapid technological development may represent not the beginning of our cosmic journey, but a return to capabilities and knowledge that we once possessed on a much grander scale. The hypothesis suggests that human consciousness preserves the inherited memories and capabilities of a civilization that once managed technological systems spanning an entire superplanet. Our instinctive drives toward space exploration, planetary engineering, and cosmic-scale manipulation may represent the awakening of inherited knowledge systems that evolved over millions of years on the original world before its catastrophic destruction. The preservation of advanced biological and technological systems through planetary destruction and reassembly indicates that cosmic catastrophes may serve as mechanisms for distributing rather than destroying complex systems. The violent fragmentation of advanced worlds may represent a natural process for spreading complex civilizations across multiple planetary bodies, increasing their resilience to future catastrophic events. The discovery that Earth formed through fragment merger rather than gradual accretion suggests that our planet's exceptional habitability may result from the beneficial combination of systems and materials from different regions of a much more advanced parent world. Earth may represent an optimized hybrid planet that combines the best characteristics of multiple different planetary environments that existed within the original superplanet's diverse geological and biological systems. The biological evidence for inherited evolutionary systems suggests that life on Earth began not with simple chemical evolution but with sophisticated biological systems that had already evolved over much longer timescales on the parent superplanet. Earth's remarkably rapid development of complex life and intelligence may reflect the activation of biological potential that was preserved during the planetary destruction and reassembly process. The consciousness evidence suggests that human intelligence and awareness may preserve mental capabilities that evolved under the much more challenging conditions of managing civilization on a massive superplanet. Our cognitive capabilities may far exceed what would be needed for survival on current Earth, because they inherited the intellectual requirements for managing planetary-scale technological systems and cosmic-scale challenges. The technological evidence indicates that human civilization may be following a developmental pathway that was established by previous civilizations on the original superplanet. Our rapid technological acceleration may represent not innovation, but rediscovery of capabilities and knowledge that were lost during the planetary destruction but preserved in inherited information systems that guide our technological development. The social evidence suggests that human civilization capabilities may be designed for managing populations and resources at scales much larger than current Earth can support. Our instinctive orientations toward global cooperation, planetary resource management, and cosmic exploration may reflect inherited social technologies that evolved for managing civilization distributed across multiple planetary fragments. The spiritual evidence indicates that human consciousness may preserve direct experiential memories of the cosmic scale events that shaped our origins. Our universal spiritual concepts of world destruction, cosmic rebirth, and planetary transformation may reflect inherited memories of the actual events that destroyed the superplanet and created our current fragmented solar system. The mathematical evidence reveals that the current solar system configuration represents not a random arrangement of independently formed planets, but an organized structure that preserves the gravitational and orbital relationships of fragments from a single destroyed superplanet. The inner planets continue to interact as components of a distributed planetary system that maintains structural unity across vast distances. The quantum evidence suggests that information and organization can be preserved across cosmic catastrophes through quantum field effects that transcend individual material structures. Complex systems may achieve forms of persistence that allow them to survive and reconstitute themselves even after the complete destruction of their original physical substrates. The galactic evidence indicates that planetary destruction and reassembly may represent common processes in cosmic evolution, serving as mechanisms for distributing and preserving advanced civilizations across multiple worlds and star systems. The violent transformation of single-planet civilizations into distributed multi-planet systems may represent a natural evolutionary progression that enhances the long-term survival prospects of complex systems. The consciousness preservation evidence suggests that intelligence and awareness may achieve forms of continuity that transcend the destruction of individual biological organisms or even entire planetary biospheres. Mental phenomena may operate through quantum field effects that can survive cosmic catastrophes and re-establish themselves in new physical substrates on reconstructed worlds. The technological survival evidence indicates that advanced engineering systems may be designed with capabilities for surviving planetary destruction and continuing their operations on reassembled worlds. The most sophisticated technologies may achieve forms of persistence that allow them to maintain their functions and continue their development even after the complete transformation of their original planetary environments. The discovery of the shattered world hypothesis represents more than a revision of Earth's origin story. It reveals that our planet and our civilization may be part of a much larger and more ancient heritage that connects us to cosmic processes and civilizations that operated on scales we are only beginning to imagine. We may be the inheritors of a legacy that spans not just millions of years of Earth history, but billions of years of cosmic evolution involving multiple generations of planetary civilizations. Our current rapid advancement toward spacefaring civilization may represent not humanity's first venture into the cosmos, but our return to a natural state of cosmic citizenship that we once possessed. When our ancestors managed civilization across the vast expanses of the original superplanet, the technologies we are developing, the challenges we are facing, and the goals we are pursuing may all represent the awakening of inherited capabilities that were preserved through the cosmic catastrophe that shattered our original world. The responsibility implications are profound. If we truly represent the reconstructed fragments of an advanced cosmic civilization, then our current choices and actions may determine not only the future of human civilization, but the continuation of a cosmic heritage that has survived planetary destruction and billions of years of cosmic evolution. We may be temporary custodians of knowledge, capabilities, and responsibilities that extend far beyond our individual lives or even our species' existence. The opportunity implications are equally significant. If our consciousness and capabilities truly preserve the heritage of a superplanetary civilization, then humanity may possess latent potentials that far exceed what we have yet discovered about ourselves. Our cognitive capabilities, technological instincts, and social coordination systems may contain inherited tools for managing challenges and achieving accomplishments on cosmic scales that we have not yet learned to access or utilize. The future implications suggest that humanity's destiny may involve not just the exploration and colonization of other worlds, but the reconstruction and expansion of the distributed planetary civilization that was scattered by the destruction of our original super. Our natural drive toward space exploration and planetary engineering may represent inherited programming that guides us toward reuniting and expanding the fragmented civilization of our cosmic heritage. The shattered world hypothesis reveals that we live not on a young planet in an empty cosmos, but on an ancient reconstructed world that preserves the heritage of civilizations that once operated on scales that spanned entire planetary systems. Our world is not an accident of cosmic evolution, but a carefully preserved fragment of a much larger and more magnificent civilization that sacrificed itself to ensure that its knowledge, capabilities, and consciousness would survive to continue the great work of expanding intelligence throughout the cosmos. We are the children of a shattered world, inheritors of a cosmic legacy that we are only now beginning to understand and reclaim.